are going to address the third day of this faculty development program organized by our PG and Research Department of Mathematics. So I request our assistant professor, Dr. Pandi Selvi, to welcome the gathering, please.
Good afternoon to each one of you. It is a moment of extreme pleasure to welcome the guests who are present here to attend this faculty development program. On behalf of the institution, I offer my regards to all the professors and the other faculty joining us. I convey my regards to the chief guest of the day, Dr. Sivanyanam. Thank you so much, sir, for accepting our invitation and talking over for the FDP. I wish this FDP enlightens us all. Thank you to everyone who made this FDP possible with their opinion and views. Thank you, sir.
Thank you, Dr. Pandi Selvi, for giving a wonderful welcome address. Now it's the time to introduce our today's resource person, Dr. C. Sivanyanam, who's having a meticulous profile with him. He has completed his master degree and MPhil degree from Madurai Kamaraj University in the year 1993 and 1995 respectively, and completed his doctoral degree under the guidance of Professor S. Arumugam from Anna University, Chennai in 2009. His research area is domination in graphs. He has worked in different institutions in India and also in Bahrain and Oman over 26 years. He is now currently working as an assistant professor of mathematics in University of Technology and Applied Sciences, Sir Sultanate of Oman. He has published more than 60 research papers in various international and national journals. He has also co-authored a book for engineering mathematics. He evaluated more than 10 PhD theses from different universities. He is also an editor-in-chief of the journal International Journal of Applied Graph Theory. So today we have a wonderful resource person. So I request Dr. Sivanyanam to deliver his lecture in our faculty development program. Please, sir.
Thank you, Professor Jackson, for your nice words. Respected people in this faculty development program, principal, management authorities, head of mathematics department and faculty members of mathematics department of V.O.C. College, and participants in this faculty development program. Very warm good evening to you all, and wishing you a great day. I'm thankful to the organizers of this faculty development program for giving me this great opportunity to meet you all. So in this talk, we are discussing about domination related parameters in graph. So what is basically graph we know? Graph G is a collection of vertices and edges. The vertex set is denoted by capital V and the edge set is denoted by capital E. The number of vertices in a graph is denoted by En and the number of edges in a graph is denoted by Em according to chart. So see this example. This is an example of a graph. So here we are having 6 vertices A, B, C, D, E and F and 8 edges available. So here n equal to 6 and m equal to 8. The number of edges incident with the vertex is called the degree of the vertex and is denoted by d of v or deg of v. Any notation we can follow. We can find out degree of all the vertices easily. Among the degrees, the maximum degree of the graph is denoted by capital delta and the minimum degree is denoted by small delta. So in this previous example, you can see degree of the vertex A is 3, degree of the vertex B is 3, degree of vertex C is 2, degree of vertex D is 4, degree of vertex E is 3, and degree of the vertex F is 1. Among these degrees, 4 is maximum. That is why delta of this graph, maximum degree of this graph equal to 4, and small delta, minimum degree of this graph equal to 1. If degree of a vertex is 0, then it is called an isolated vertex. And if the degree of a vertex is 1, then it is called a pentane vertex. The vertex adjacent to the pentane vertex is called a support vertex. In a tree, pentane vertex is also referred as a leaf. D of u comma v, what is the meaning of this? The distance between u and v. So d of u comma v is the length of the shortest uv path. So in between u and v, we can find out any number of paths. So the length of the shortest uv path is called the distance between that two vertices. A neighbor of a vertex v is a vertex different from v that is adjacent to v. So what are the vertices adjacent to v are called neighbors of that vertex. The same thing we can say in other way. If distance between u and v, d of u comma v equal to 1, distance is 1, then we can say v is a neighbor of u. So neighbor of u is denoted by the notation n of u. N of u means set of vertices v such that distance between u and v equal to 1. Anyway, we can say, different way we can say the definition of the neighbor. Now the neighborhood set. What is the meaning of the neighborhood set? The neighborhood set of a set S. S is a set of some vertices of the graph G. So the neighborhood set of a set S is the set of all neighbors of vertices in S and is denoted by n of S. So each and every vertices we can find out the neighbors. So make a set for these neighbors. It is called a neighborhood set. And we denote this by ns. That is ns equal to union of n of u for all u belongs to S. For each and every vertex in S, we can find out the neighbor, take union. That is called ns. Okay, for neighborhood set of a set in S. So using this concept only, now we are going to think about the domination parameters. So before that, some basic domination parameter I will explain. What is the meaning of dominating set? Everyone know this. A set S, which is a subset of the vertex set V, is called a dominating set if every vertex in V minus S is adjacent to a vertex in S. Every vertex in the complement of S having at least one neighbor in S. That is another meaning. The same thing we can say in other way. Set S is a subset of V if the closed neighborhood set S is equal to V. What is the meaning of closed neighborhood set mean? First you have to find out neighborhood set of S, that is NS, open bracket we can use. All the neighbors of the vertices of S. Then union S, that is closed neighborhood set of S, which is equal to the whole vertex set V. If you are getting like this, then we can say S is your dominating set. Okay, dominating set, a different way we are defining. So the minimum cardinality of a dominating set is called the domination number of a graph G. Because for any graph, we can find out more than one dominating set. Among all the dominating sets, we can find out the minimum cardinality dominating set. The minimum cardinality is called the domination number of that graph G. We can denote this by gamma of G. Okay, gamma means domination number. So I'm giving an example. It is a cycle C7. Okay, the cycle on 7 vertices is the example. So here vertices are A, B, C, D, E, F, G, like that I'm labeling. We are assigning the name for the vertices. Here you have to see these blue color vertices I'm considering. A, D, and F, I have to make a set. This is set of S. So S is a set containing the vertices A, D, and F. Okay, so we have to see the black color vertices. You can see it is outside of S. All the black color vertices having at least one neighbor in blue color vertices. So all the black color vertices are adjacent with at least one blue color vertices. That is why the set of blue color vertices is a dominating set. So S is a dominating set of the cardinality 3. So what is the minimum cardinality of this? How we are finding? Suppose I am considering one vertex. Suppose one vertex you have to consider in this cycle. That vertex is adjacent to two vertices. So one vertex is dominating to two vertices other than that vertex. Including that mean, so one vertex dominating three vertices. So if we are taking one vertex, it is dominating maximum three vertices. If you are taking two different vertices, it dominating maximum 6 vertices. So two vertices dominating set, a dominating set which containing two vertices is impossible here, because this graph containing 7 vertices. So we need another one vertex compulsory. So S is your dominating set of minimum cardinality here, and hence gamma equal to 3. Like that we have to find out the domination number for any graph. Okay, so easy example I gave to you. So now you have to take this example. So one big graph we are having. Here also two different colors I gave. You have to consider all blue color vertices. So that is a set S. So S is a set of blue color vertices in this graph. And all black color vertices are available in outside of S, complement of S. And you have to see all the black color vertices having at least one neighbor in S. S is a set of blue color vertices. So this blue color vertices is a dominating set. So S containing here 5 vertices. Is it minimum? You have to check that in this graph. This vertex G, F, H, like that. These vertices you can consider. These are pendant vertices. If you take one pendant vertex in graphene, either that pendant vertex will be available in S, dominating set, or the corresponding support should be available in S, dominating set, any one of that. So here we have 3 pendant vertices in the first corresponding to E is a support. So corresponding to E, we are having 3 vertices. So either these 3 vertices should be available in S or E should be available. but we want to find out minimum cardinality dominating set, and hence I am taking G. Similarly, you have to see K, L, P, B. So it is compulsory either P or P should be available in S, K compulsory available in S, L compulsory available L or M. Okay, any one compulsory available in S, E should be available in S. So this blue color vertices is a set of dominating vertices having minimum cardinality. So it is a dominating set with minimum cardinality, and hence gamma equal to 5. So Kn mean complete graph on n vertices. So domination number of a complete graph is 1. What is the meaning of complete graph? We know every pair of vertices are adjacent. And already I gave the example for C7, cycle on 7 vertices. Now in general, cycle on n vertices, domination number is upper integral n by 3. And domination number of path Pn. The domination number of a path on n vertices is upper integral or ceiling function n by 3. And domination number of a complete bipartite graph. Okay, R and S are the number of vertices in the bipartition, and R is greater than S, and R and S greater than or equal to 2. Both are greater than or equal to 2 mean we need 2 vertices, otherwise one vertex is enough. Now, what usually the others are doing, we have the definition of the dominating set and domination number. In this dominating set, they are imposing extra condition, additional condition they are imposing. So now first condition, it is independent. What is the meaning of independent set? A set of vertices, when we say this, it is an independent set. So independent set means we have to draw the induced graph of that. We are getting empty graph, one case, and no pair of vertices are adjacent in G. No pair of vertices in that vertex set not adjacent in G. Then it is called independent set. Okay, any 2 vertices we have to take in G, and particularly in S, that vertices are non-adjacent. Okay, and we can say it is a stable set also. So a independent set as well as dominating set. First, it is a dominating set, and it is an independent set. Then it is called independent dominating set. So the minimum cardinality of any independent dominating set is called independent domination number, and we denote this by I of G. So in this graph, you have to see this. Already I gave this example, domination number gamma equal to 5. Here E and K are adjacent, K and L are adjacent, B and P are non-adjacent. Okay, so but this K, suppose I remove this K from this set, blue color vertices set, we have to include some other vertices, then automatically it should be independent set. Instead of K, I am taking I and J. I am removing K from this, including I and J. Now we have to see it is a dominating set, and no pair of vertices are adjacent. No pair of vertices are adjacent. So it is an independent dominating set, and hence I of G, independent domination number, is equal to 6 here. Like that, we have to imposing another condition. Instead of independence condition, we are imposing connected condition. Dominating set we have to take. Corresponding dominating set induced graph we have to find out. If the induced graph is connected graph, then we can say the dominating set is connected dominating set. Okay, so first we have to find out a dominating set S. That S, the induced subgraph of the original graph G, we can identify. If that graph is connected, then we can say it is a connected dominating set. The minimum cardinality of a connected dominating set is called the connected domination number of G, and is denoted by gamma C of G. Again, I am giving the same example. How to see here, it is a dominating set. Blue color vertices denote the dominating set. Suppose I am drawing the induced graph of this blue color vertices mean here one P3 I am getting EKL. Induced graph mean EKL. E is adjacent to K, K is adjacent to L. It is one path on 3 vertices and the extra 2 vertices B and P. It is K2. So it is a isolated vertices we have. So we are having 3 components. It is a disconnected graph with 3 components. And hence it is not connected. I want to make it connected. How I can make it connected? You can see I'm including extra 2 vertices. I can include this C and D. I can include R, O and N. I can include anything. Okay, I'm including O and N. Now you can see it is containing this blue color vertices contain a single component. A single component, only one component, and hence it is connected. So it is a connected dominating set. It is a connected dominating set, and hence gamma C equal to 7 here. So instead of connected, we have to relax the definition. Okay, so connected is not necessary. At least we have to find out the induced graph of the dominating set. That induced graph contains no isolated vertex. Like that, no need connected. Okay, connected is not necessary. It may be disconnected, acceptable. But it not containing any isolated vertex, then we can say it is called total dominating set. Okay, a dominating set, yes, I have to take. You have to draw the induced graph of the dominating set, yes. We can identify the induced graph having no isolated vertex. Then we can say it is by total dominating set. The minimum cardinality of a total dominating set is called a total domination number, and we can denote this by gamma T of G. Okay. So we have the example, again the same example. We have to see here, it is a dominating set, blue color vertices. That set is a dominating set, and domination number equal to 5. Is it a total dominating set? We have to check. So here you have to draw the induced graph mean here P3 we are getting, B and P are isolated vertices here. So we need no isolated vertex in that set. What I can include here, extra only one vertex I can include, O, in this set. Then automatically it is a disconnected graph. No need we have connected. Okay, so it is a disconnected graph. But what we need, it contains no isolated vertex. So now we are having here one P3, here another P3. So 2 P3s are available. It is a disconnected graph, but it contains no isolated vertex, and hence it is a total dominating set. Gamma T of this graph, total domination number of this graph equal to 6. Okay, so like that we are defining different condition on S. We are getting different domination parameter. Now what we have to think about that, already we have one definition. If S is a set of vertices, some set of vertices, then we can find out NS. NS means neighborhood set of S. So now I am considering S is a dominating set. NS we can find out. I am imposing condition on NS. Previously we are imposing condition on S. S is independent, S is connected, induced S is connected, and induced S contains no isolated vertex. Like that, lot of domination parameters available. Here we are imposing condition on neighborhood set of this dominating set, yes, NS. So S is a dominating set. We can find out NS. NS means neighborhood set of S. That NS we can find out, we can draw the induced graph. We can draw the induced graph, or we can find out the induced graph. NS, induced NS. That graph may be connected, disconnected, or may be contain total isolated vertices, or may not contain isolated vertices. So now we are considering these two concepts in induced NS. Connected and no isolated vertices. So first one is connected. Okay, so we have S is a dominating set. We can find out the NS. Induced NS is connected. Then we can say dominating set is neighborhood connected dominating set. Okay, S is a dominating set. Induced NS. NS is, we can find out NS. NS means neighborhood set of S. Then induced NS we can find out if it is a connected graph. Then we can say the dominating set is neighborhood connected dominating set. So among all the neighborhood connected dominating set, we can find out the minimum cardinality neighborhood connected dominating set. Neighborhood connected dominating set, we can say shortly NCD set. Okay, so minimum cardinality NCD set, we can find out that minimum cardinality is called neighborhood connected domination number or NCD number. We can denote this by gamma NC. We can denote this by gamma NC of G. So see this. This is a graph, front sheet graph. What is the domination number of this graph? This vertex, center vertex, you can see A. If I'm selecting this vertex A, it is dominating all other vertices. It is dominating all other vertices. So domination number is 1 for this graph. Domination number is 1. Okay, so S is a set containing only one vertex A. So S is a singleton set. What is NS here? Other than A, all the vertices are available in NS. If I am taking S equal to singleton set A, mean NS is all other vertices, outer vertices in this graph. So only the outer vertices is available in NS. So induced NS mean what we are having? 4 times K2. So 4 times K2 we are getting. It is a disconnected graph. It is a disconnected graph. So here BC is 1 K2, DE is another K2, FG is another K2, HI is another K2. So 4 times K2 we are having. So it is a disconnected graph. So we want to make it NS is connected. S is a dominating set. NS, induced NS should be connected. Mean what I am taking extra one vertex I am taking in S. Already A is available in S. Now I include the vertex B. A and B I am taking. So S is a set containing the vertices A and B. S is a set containing the vertices A and B. So now what is NS? For A, all the outer vertices are available in NS. For the vertex B, neighbor is A and C. So now union we have to take A neighbor, union B neighbor, mean whole vertex that we are getting. So we are drawing the graph for this, mean the whole graph again we are getting G. So it is a connected graph automatically. So gamma NC of G equal to 2. So neighborhood connected graph defined only for connected graph. Neighborhood connected dominating set defined only for connected graph. Okay, for disconnected graph, it's not available. Now the same idea, neighborhood total dominating set. What is it? Neighborhood total dominating set? Already I told you. S is a dominating set. We are imposing condition on induced NS. So induced NS having no isolated vertex. Then the dominating set S is called neighborhood total dominating set. Shortly we can say NTD set. NTD set. Okay, neighborhood total dominating set. So what is the meaning of this? It is a dominating set. Yes. Induced NS we can find out. If induced NS having no isolated vertex, then we can say it is a neighborhood total dominating set. Shortly NTD set. So minimum cardinality of the NTD set is called neighborhood total domination number. And we denote this by gamma NT. Gamma NT. So again, I am giving the same example. You have to see gamma. What is the gamma here? Gamma equal to 5. I am taking S is a set of blue color vertices. All the black color vertices should be available in NS here because S blue color vertices are dominating set. All the black color vertices should be available in NS because all the black color vertices are neighbors of the blue color vertices. Okay, so NS containing all the black color vertices, and because here E is a neighbor of K, E should be available in NS. K is the neighbor of E and L, K should be available in NS. L is a neighbor of K, L is also available in NS. So here S is a set of blue color vertices And what is NS? NS is a set of black color vertices union EKL. Set of the vertices EKL. Okay. So now NS, imagine it. NS is not available. NS not containing B. NS not containing P also. So, but the A is available in NS. This Q is available in NS. O is available in NS. You have to see this in NS. O is not adjacent with any vertices in NS because B and P are not available in NS. A is isolated vertex in NS. Q is isolated vertex in NS. So this A, O, Q are isolated vertices in NS. Remainings are not isolated, adjacent to some vertices in NS. So we have to make it this, we have to avoid this isolated vertices, or we have to delete this from NS. How we have to delete this mean? We have to include this vertex O. Now we have to see what is NS. All black color vertices are available in NS first. So NS is equal to black color vertices set union blue color vertices set EKL BOP. So what is totally we are having B. So induced B we are drawing the original graph we are getting. It is a connected graph and automatically containing no isolated vertices. And hence gamma NT of this graph equal to 6. Gamma NT of this graph equal to 6. This is again the same example I am giving to you. What is gamma NT of this graph? Gamma NC, neighborhood connected domination number, is equal to 2. Already I explained that. Now gamma NT of G mean only A I am considering. S is a set containing, or S is a singleton set containing the vertex A. So A is dominating all vertices, all outer vertices. Okay, so NS is a set containing all the vertices other than A. So outside vertex you have to see BC. B is adjacent with C. C is adjacent with B. So it is not isolated. Similarly, D and E are adjacent. That's why D and E are not isolated. G and F are not isolated. I and H are not isolated. So NS contains no isolated vertex. So only one vertex is sufficient for neighborhood total dominating set. Okay, so gamma NT of this graph equal to 1. So now what we have to think about that, one neighborhood total dominating set I am taking, it compulsory a dominating set. Okay, that is why domination number is less than gamma NT. Any neighborhood total dominating set with the minimum cardinality even you have to take it, that compulsory a dominating set, but domination number may be less than that. Hence gamma is less than or equal to gamma NT. Similarly, you have to see every total dominating set is a neighborhood total dominating set, and hence gamma NT is less than or equal to gamma T. Okay, gamma NT. So upper bound is gamma T, lower bound is gamma. So gamma NT is available in between gamma and gamma T. May be equal also sometime. What is the upper bound in terms of the number of vertices? So I'm taking a connected graph G. What is gamma NT of G? It is less than or equal to ceiling function of n by 2 or upper integral of n by 2. And we can characterize this when we are having upper integral n by 2. Suppose n is odd number, upper integral of n by 2 means n plus 1 by 2. So maximum value is n plus 1 by 2. So continuation of this theorem, let G be a connected graph of order n greater than or equal to 3. Then gamma NT of G is less than or equal to n plus 1 by 2. The same thing only. If n is odd, we are getting n plus 1 by 2. With the equality, when these two are equal, when this inequality is sharp, if and only if G is either C5 or subdivided star. So subdivided star means one star graph we have to draw. All the edges should be subdivided by one vertex. Okay, that is subdivided star. So only these two graphs we are having gamma nd of g is equal to n plus 1 by 2, remaining all less than this one. This is a basic definition matching. What is the meaning of independent set? Already I gave to you. Independent set is a set of vertices such that no pair of vertices are adjacent. Similarly, matching means it is a set of edges such that no pair of edges are adjacent in G. A matching in G is a set of pairwise independent edges. Okay, it is a independent edges pairwise. Every pair of vertices are, every pair of edges are non-adjacent. So matching of maximum cardinality is called a matching number and is denoted by alpha dash of G and is denoted by alpha dash of G. This graph you have to see. Again, I am taking the same graph. What is a matching number here? So you have to find out set of independent edges. So edges we have to find out, and no pair of edges are adjacent. So suppose I am taking this B and C is one edge mean. I cannot take this AC and AB. So I am considering B and C one edge. So then any one of these two edges I can take, or this edge I can take. Okay, DE I am taking. Similarly, GF, HI. These edges I am considering outer four edges. Okay, so it is unmatching. So if you have to add any more edges with this set, then automatically that edge is adjacent with any one of these edges. So maximum 4 edges we can find out that are independent edges. So and hence alpha dash of G equal to 4 in this graph. Okay, that is the meaning of a matching number. Next we have path cover. What is the meaning of path cover? One graph we are having. We have to find out different paths in the graph. Each and every vertex should be available in a distinct path we have to take, disjoint path. So one path, vertex disjoint path. One path we have to take. Another path if you have to take means that vertices are not available in one path. If it is available in one path, then that is not available in another path. So vertex disjoint path we have to take. Okay, so collection of all vertex disjoint path you have to take. That is called a path cover. What is a path covering number? The cardinality of a minimum path cover is called path covering number. We have to denote this by PC of G. PC of G. You have to see again the same thing. Here, how many paths we have to find out such that each and every vertex available in exactly one path. So I'm considering this BCA. This is one path. Okay, BCA is a path. Don't go for induced graph. Okay, just a path. BCA. So 3 vertices available. So it is one path. Now we have to take another one path. Suppose I am taking H, A mean A already taken. So this side I am taking one path mean this is another path only, because A already available in one path. So IH is one path, DE is one path, GF is another path. Okay, here also we are having 4 paths. So PC of G equal to 4. So now why I am giving these two definitions, matching number and path covering number, mean what is the relationship between this neighborhood total domination number and these two parameters. So we have, before that we have, what is the path covering number of Pn, what is path covering number of Cn, what is path covering number of Kn, these are all 1. And path covering number of complete bipartite graph is 1 or S minus R. 1 when it is possible, R value is either S minus 1 or S, then it is 1. R value is less than S minus 1, then it is S minus R. Okay, then it is S minus R. So this is a path covering number. Now we have to see the relationship between this neighborhood total domination number and matching number with the path covering number. I have to consider a connected graph G with at least 3 vertices. Then this gamma nt of G is less than or equal to alpha dash of G plus half of PC of G, sum of matching number and half of path covering number is an upper bound of neighborhood total domination number, unless other than this graph P3, P5, C5, other than these 3 graph, it is satisfied. Okay, this is an upper bound. So like that, any parameter we are having any domination parameter, we can find out the upper bound and we can characterize when we are having equality possible. We can characterize like this. So after domination number, what next we are having, it is called Dometic number. We are having the graph G. It should contain the vertex set V. The vertex set can be partitioned into the classes V1, V2, Vk, like that, with the condition that each class is a dominating set. Each class is a dominating set. Like that, we have to partition the vertices of the graph. It is called a Dometic partition. A Dometic partition of G is a partition V1, V2, Vk, in which each Vi is a dominating set of G. Each Vi is a dominating set. Like that, we have to find out the partition. Then this partition is called Dometic partition. Lot of partition we can find out, lot of Dometic partition we can find out, because the vertex set V itself is a dominating set. So Dometic partition with only one class is possible. Only one class is possible. That is why we are finding one is obvious one. Only one class is obvious. So we have to try to find out more than one. So more than one means which one is maximum, we have to think about that. The maximum order of the Dometic partition is called the Dometic number. Domination number means minimum cardinality. Here, Dometic partition maximum. Okay, maximum order. And it is denoted by D of G. So, okay, in the vertex set, we have to partition into dominating set. The Dometic, it is called Dometic number, Dometic partition, and the maximum order is called Dometic number. Okay, this is a base concept. So in this case, here also we can impose a condition. Each class may be a connected dominating set. Then it is called connected Dometic partition. Each class is a total dominating set, means total Dometic partition. Like that, we have the concept. We have the example here. Suppose I'm considering this graph. Okay, this graph containing 6 vertices and 8 edges. Now I have to find out the classes of vertex set, such that each class should be a dominating set. Like that, you have to find out. Try to find out maximum dominating sets. Here V containing 6 vertices. So these 6 vertices we have to partition into classes. How many classes maximum possible such that each class should be a dominating set? Here you have to take, I have only 2 classes, V1 and V2. V1 is the set containing the vertices A and E. V1 is a set containing the vertices A and E. You have to check that this A and E, this V1 is a dominating set or not, because C, D, B, F, these vertices having adjacent with the adjacent vertices A and E. Okay, this B, C, D, F. These are adjacent with any of A and E, or both also. So A and E is a dominating set. So now we have to find out another class that is also a dominating set. Means we can find out here F compulsory we have to take. This F compulsory we have to take, because F dominating already we found E. So now F compulsory we have partition. Now F compulsory we have to take. If I am taking F, if we need third partition means E and F cannot be available. For dominating F, there is nowhere. And hence we have maximum of 2 dominating sets only available. So remaining I have C, D, B and F I am taking. B, C, D and F. This also a dominating set. So V1 and V2 are dominating set, and this is V1 comma V2, that partition is a dometic partition. And more than this we cannot find out, V1, V2, V3, like that we cannot find out. Maximum 2 disjoint dominating set only we can find out here, and hence dometic number of this graph equal to 2. Now to see, for this graph also, I have here A and B. A and B is a one dominating set. Remaining this all pendant vertices should be available in one dominating set. So here also V1 comma V2, V1 containing the supports A and B, V2 contains the pendant vertices C, D, E, G, F, H. So these two classes V1 and V2, it is a dometic partition of maximum order, and hence here also D of G equal to dometic number of this graph equal to 2. Already I told you, we have to imposing condition, extra condition. Previously we have a partition with each class is a dominating set. Now here also partition of the vertex set with each class is a total dominating set. Okay, so one partition we are having, partition of the vertex set, it containing classes, each class is a total dominating set, and hence this partition is called total dometic partition. Here also the maximum order of the total dometic partition is called total dometic number, and we denote this by dt of G. dt of G. Now to see this example, here also we have like this. A and B I am taking. A and B are adjacent. A and B I am taking here. Okay, A and B I have to take. This is dominating remaining all vertices. Remaining all vertices. So A and B I can take. D and C I can take. Okay, this is A and B dominating all other vertices. D and C I am taking all other vertices. So A and B available in one class. D and C will be available in another class. So third class should be containing E and F. But E and F is a dominating set here, no problem. But E and F, that set, the set containing the vertices E and F is not a total dominating set. So E and F should be available in any one of these two vertices, A, B set or DC set. So I am taking A, B set separately. V2 is another set which containing the vertices C, D, E, F. These two are total dominating set. And this partition V1 comma V2 is a total dometic partition of maximum order. Here also total dometic number is equal to 2. This graph what we have. Previously dometic partition I said it is 2. Now I am taking here this A and B is a one set. It is a dominating set and a total dominating set. So one set I can take this A and B. Remaining set I can take this all the pendant vertices. It is a dominating set, but it's containing isolated vertices C, D, E, G, F, H. These are isolated vertices, and hence it should be included in this A set. So only one class we are getting, and hence here total domination number total dometic number equal to 1. Similarly, connected definition. It is a partition of the vertex set. Each class is a connected dominating set. Then it is called connected dometic partition. The maximum order of the connected dometic partition is called connected dometic number. We denote this by DC of G. Okay, so you have to see this example again. Here you have to see this AB only. AB is a connected, DC is connected, and E and F mean it is disconnected. So this E and F should be available in V2 or V1. So here also connected dometic number is equal to 2. For this graph, connected dometic number is equal to 1. The same idea. Now we have our concept neighborhood connected dometic number. What is the condition here? It is a partition of the vertex set. Each class should be a neighborhood connected dominating set. Each class should be a neighborhood connected dominating set. Previously dominating set, second one is connected dominating set, third one is total dominating set. Now we are having NCD set. Each VI is a NCD set. So like that we have the partition. That partition is called neighborhood connected dometic partition. And the maximum order of this neighborhood connected dometic partition is called neighborhood connected dometic number. We have to denote this by DNC of G. DNC of G. Okay, so you have to see again the same example, but here you have to see this graph. Already I told you for this graph, connected dometic number is 2. Total dometic number is 2. But now we have neighborhood connected dometic number. Here we have 3 classes. A, B is one class because it is a dominating set. D, C or C, D available in one class. C and D dominating all other vertices. And E and F, this also dominating set. So 3 dominating set. Now we can find out what is NS. Suppose I am taking A and B, that is our V1. A neighbors are E, D, C. Sorry, A neighbors are E and D. B also. A neighbors are B, E, D. B neighbors are A, C, F. So what are the neighbors of A and B mean? All the vertices we are having. So AB is a neighborhood connected dominating set. Similarly, DC is a neighborhood connected dominating set. Now AB over, DC over. Now we have to think about E and F. E dominating A and D, F dominating B and C. Okay, so all the vertices E and F are dominating set. What is a neighborhood set mean? E neighbors are A and D, F neighbors are B and C. So the induced graph NS here is A, B, C, D. So square we are having, it is a connected graph. So E, F, the set of vertices containing E and F, that is V3, is a neighborhood connected dominating set. So here V1 is AB, V2 is CD, and V3 is EF. So we can split into 3 classes. Each class is a NCD set. And hence here DNC. DNC means neighborhood connected dometic number of this graph equal to 3. For this graph you have to see here again 2. Because this A and B I have to take me. What is neighbor? Whole set we are having. Neighborhood set is whole set. Whole graph we are having for NS. Okay, for A and B. And the remaining vertices we are taking in this remaining vertices C, D, E, G, F, H. That is vertex set V2 if I am taking. Then what is N of V2? It is A and B. So that is also connected. So V1 is A and B. V2 is remaining the set of pendant vertices. Okay. So these 2 vertex sets are NCD set. And hence V1, V2 is a neighborhood connected dometic partition and with maximum order. And hence DNC is equal to 2 here. For this graph you can see friendship graph. Only A, if I am taking, it is not a NCD set. Because already I told you for this graph, gamma NC equal to 2. Okay, so A and B, so minimum 2 vertices we need for every NCD set. So A and B, I have to take as a one NCD set. So this C should be available in any class. If C is available, for adjacent with C, we need one vertex. But it's not available here because B and A already available. Okay, so remaining C, D, F, G, H, I have to take remaining everything as a single vertex set. Okay, so V1 and V2 we have to take it. V1 and V2, and hence the D and C of G equal to 2 here. Only 2 we can take it. Similarly, neighborhood total dometic number. What is this? It is a partition. Each class of the partition should be a NTD set, neighborhood total dominating set. And then it is called neighborhood total dometic partition. The maximum order of neighborhood total dometic partition, shortly we can say NT dometic partition or NT dometic partition. We can say that NT dometic partition maximum order is called neighborhood total dometic number. Shortly we can say NT dometic number of G, and is denoted by DNT of G. Now we have to study the properties of this neighborhood total dometic number. Before that, we have the same example again. Here AB is a one NTD set, CD is one NTD set, EF is another NTD set. All are NTD set. So here DNT equal to neighborhood total dometic number equal to 3. Here you can see, here also AB is your neighborhood total dometic dominating set, and remaining this pendant vertices is a neighborhood total dominating set. So only 2 neighborhood total dominating set we can find out, and hence DNT equal to 2 here. For this graph, TNT you have to see A, I have to find out A singleton set A. Okay, so this is a NTD set. A only I have to consider it is a NTD set. Okay, A only. So V1 is a singleton set containing A. Now V2, this outer vertices, any one of the vertex you have to select, either B or C. I'm selecting B. It is dominating C and A. I'm selecting D. It is dominating E and A. I'm selecting F. It is dominating G and A. I'm selecting H. It is dominating I and A. Okay, so what is N in V2? I'm taking B, D, F, H. Mean what is N of V2? We are having N of V2 mean C, A, E, G, I. These we are taking. So automatically we are having one star graph, and hence it's not containing any isolated vertices. So this BDFH is a NTD set. Similarly, CEGI remaining vertices. This also another NTD set. So totally 3 disjoint NTD set we can find out maximum, and hence DNT equal to 3 here. Okay, neighborhood total dometic number of this graph equal to 3. So what are the observations we have from this? Only neighborhood total dometic number. Any dometic partition of complete graph is also a NT-dometic partition, because complete graph means each and every vertex separately we can take it. Okay, every vertex is a dominating set. Every vertex set is every singleton set is a dominating set. And hence here DNT of Kn equal to D of Kn, which is equal to En. So neighborhood total dometic number of a complete graph is equal to En. Similarly, we can say DNT of complete bipartite graph, which is equal to dometic number of a complete bipartite graph, both are equal, which is equal to minimum of Parker minus. Wheel graph, DNT of Wen, which is equal to D of Wen, which is equal to either 4 or 3. If n congruent to 1 or 3, we are getting 4, otherwise we are getting 3. Another observation, since any total dometic partition of G is a NT-dometic partition, any total dometic partition, because every total dominating set is a NTD set. So every total dometic partition compulsory NT dometic partition and NC dometic partition also. And hence we are having it is a NT dometic partition. We have dt of G. dt of G means total dometic number of G is smaller than neighborhood connected dometic number of G, which is smaller than neighborhood total dometic number of G, and the maximum is dometic number. Okay, so upper bound is dometic number. Then after that we are having neighborhood total dometic number. Then after that we are having neighborhood connected dometic number. So finally, last we are having neighborhood total dometic number. So this is a chain we have. Now, what is another observation? One vertex we have with a minimum degree. So I am taking a vertex B with the minimum degree. The minimum degree is denoted by delta, already I told you. So since any NTD set must contain either B or neighbor of B. Either B or neighbor of B, and hence we are having the neighborhood total dometic number is less than or equal to 1 plus delta. Maximum delta plus 1, where one number of NTD set we can find out. More than that it is not possible. That is why D and T is less than or equal to delta plus 1. This graph you have to see. Before that we are having the definition. NT dometically full graph. What is NT dometically full graph means? A graph with DNT value is equal to delta plus 1. Already I told you DNT is less than or equal to delta plus 1. Delta plus 1 is the upper bound. Okay. So which graph having DNT value equal to delta plus 1? DNT means neighborhood total dometic number is equal to delta plus 1. That graph is called a dometically full graph. So this graph you have to see delta equal to 2 here. So DNT equal to 3, already we verified. So DNT equal to 3, so which is equal to delta plus 1. And hence it is an example for NT dometically full graph. So what is the meaning of NT dometically full? I am giving two positive integers to you, N and K. N is greater than or equal to 4, and K value lies between 1 and N. So like the two positive integers, if we have, then we can find out a graph G with N vertices. With N vertices such that the neighborhood total dometic number is equal to K. So like that we can find out the graph. If I am giving any two numbers to you, any two integers, positive integers to you, satisfying this condition, N is greater than or equal to 4, and K value available in between 1 and M, then we can find out a graph G with N vertices and DNT value equal to K. So how we are finding example is G equal to Kn. If K and N are equal, mean we have to take G equal to Kn. If K equal to 1, we need DNT equal to 1, mean we have to take star graph. Suppose the DNT value is equal to 2, we need, mean we have to take by star graph. Other than this number 1, other than 1 and 2 remaining numbers, mean we have to take this graph. Complete graph on K minus 1 vertices plus remaining vertices. Remaining vertices are isolated vertices. We are finding the plus of these two graphs. We can find out. So like this we can find out the graph. Here path on N vertices. What is the neighborhood total dometic number? So which is equal to 1 if N equal to 2, 3, 5. Otherwise it is equal to 2. And what is the neighborhood total dometic number of cycle? If it is equal to 1, if N equal to 5, it is equal to 3, N congruent to 0 mod 3. Otherwise we have 2. Okay, so easily we can find out these two. Now we have to see, I have one NT dometic partition. V1, V2, VDNT. So it is a maximum order NT dometic partition. Okay, V1, V2, VDNT mean it is a maximum order. We have each VI is a NTD set. So each VI is a NTD set means cardinality of VI should be greater than or equal to gamma NT. So each VI should be greater than or equal to gamma NT. How many VIs are available? DNT number of VIs available. That is why gamma nt multiply with the dnt, which is less than or equal to en. This is the first observation. So product of neighborhood total domination number and neighborhood total Dometic number is maximum n. Maximum n. Okay. So this example you have to see when we have maximum n. This graph, what is this graph? So it's a complete graph. So K4, 3 times K4 I am taking. So for this graph, we have to take this product equal to n. You have to see, generally I am giving, if G equal to S time KR, S time KR, S time complete graph, R greater than or equal to 3, S greater than or equal to 1, at least one complete graph we have to take. Then DNT equal to R here and gamma NT equal to S. Then product is equal to SR, SR equal to N we have. Okay, that is why I am writing here in this example. You can see N equal to 12. N equal to 12. There are 12 vertices. S equal to 3. There are 3 complete graph I am taking. And R equal to 4 here. So what is gamma NT? Each and every component I have to select one vertex for dominating. That's why gamma NT should be 3. And what is a DNT means? We have to take each and every component one vertex. So one class containing 3 vertices. So each and every component one vertex we have to take. So totally we are having 4 classes. So DNT equal to 4. Hence product equal to 12, 12 equal to n. This one example. Okay, so another example you have to see. If we have 2 complete bipartite graph with the equal number of partition weight. Okay, so here G equal to S time KRR. One partition with one class containing R vertices, another class also containing R vertices. Like that. Here in this example, both are having 3 vertices. I take here 2 S value equal to 2 here. So S time KRR. In this graph also, we are having product of Dometic number, neighborhood total Dometic number, and neighborhood total domination number equal to en. Okay, so easily we can verify this. Here also n equal to 12, S equal to 2, and R equal to 3. We can find out easily. And this graph, third graph, G equal to corona product, G1 and K1. G1 is any connected graph you have to take. And this graph, DNT equal to 2, and gamma NT equal to n by 2. So DNT multiply gamma NT equal to en. So I am giving one example. For this graph, n equal to 8 here, and gamma NT equal to 4. Either the pendant vertex available, no, either support or pendant we have to take. So one class compulsory 4 vertices, other class remaining 4 vertices. So totally 2 classes. So DNT equal to 2. So product equal to 8 we have. So the next theorem, big theorem we have. Let G be a graph with the delta equal to n minus 1. Okay, delta equal to n minus 1 means the maximum degree is n minus 1. So we can find out a vertex which is adjacent to all other vertices. That vertex is called saturated vertex, we can say. Okay, let K denote the number of vertices of degree n minus 1. So K number of vertices are available with the degree n minus 1 in that graph, in that particular graph. Then the upper bound of neighborhood total Dometic number is half of n plus k. Half of n plus k. This upper bound. Okay. So k is the number of saturated vertices we can take. When these are equal, when equality is sharp, G is equal to this graph. You have to see G equal to complete graph on k vertices plus h, where h is isomorphic to 2 times k n minus k by 2, or h is a connected graph with v of h equal to, v of h can be partitioned into vertices x1, x2, xr. These are partitioned. R value, how many partitions we are having? R equal to n minus k by 2. Each class containing only 2 vertices, xi, modulus of xi equal to 2. The induced subgraph induced by the edges of h having one end in xi, another end in xj. Okay, so 2 classes you have to select. For example, x1 and x2 I am selecting. The set of edges having one end in x1 and another end in x2, I have to select. That should form a perfect matching. So like this, if it is available, then that graph, the equality is true. So the graph is looking like this. So it is one complete graph. It is one complete graph with this complete graph with k vertices. K is the number of maximum degree, number of saturated vertices. Okay, so that kk you have to take. And one kr. What is r value? R equal to n minus k by 2. So here one complete graph, here one complete graph. So plus I am taking in this kk, all the vertices should be adjacent with all the vertices of kr, and all the vertices of kk adjacent with all the vertices of kr. Like this, you can imagine the graph. For this graph, the equality attained. The same thing. Now we have the graph with delta less than n minus 1. So the graph, the k value equal to 0 here. Delta less than n minus 1 means the graph contains no saturated vertices. Okay, k equal to 0 here. Then automatically k replaced by 0 mean what is the value we are having? K equal to 0 mean automatically dnd of g less than or equal to n by 2. That is another upper bound. dnd of g less than or equal to n by 2. Further, when equality holds, this vertex set can be partitioned into n by 2 number of classes. N by 2 number of classes. Each class containing 2 vertices. Each class containing 2 vertices. Then you can find out the edge induced graph with one end in xi, another end in xj, it having the perfect matching. And v minus xi has no isolated vertices if xi is independent. Sometimes xi is independent possible because k2 bar, xi containing 2 vertices, k2 bar is possible. So v minus xi not containing any isolated vertices, then also it is true. Now Northern Cardinality is that. One graph we have to take, that graph G. What is the condition? G and G bar both are connected. Then dnd of G plus dnd of G bar is less than or equal to En. Sum of neighborhood total domination number of G and G bar is maximum here. Then when equality holds, the same idea here also. Equality holds mean automatically dnd of G equal to n by 2 and dnd of G bar equal to n by 2. Okay, when dnd of G equal to n by 2, already we are having the same thing here also. For the equality holds if and only if V can be partitioned into the classes of vertices. How many classes? N by 2 classes. Okay, so partition already I told you. Then induced graph you have to find out xi union xj. Any two classes you have to take. Union we can find out. Then induced graph we can find out. It should be any one of these graphs. Which graph? C4 or P4 or 2 times K2. Any one of these graphs. Then only we are having this equality attained. Okay, so now I'm giving some problems to you. Still not yet solved. Characterize the classes of graphs for which the product equal to n. Some example I gave to you, but in general, dnd of G multiply gamma nd of G equal to n. Characterize this. This is one problem. And characterize NT dometically full graph. What is NT dometically full graph? I told you dnt equal to delta plus 1. So you can characterize this graph and characterize the graphs for which dnd of G equal to dt of G. Sometimes it is equal, sometimes dnd is less than I told you, less than d of G I told you. When these two are equal, we can characterize. These three problems we are having still. Okay, so and we have these are the reference. First one, second one, third one, and professor and myself writing these three papers. And these are the continuation of these three papers. So these are the references. Okay, thank you very much. Thank you for your listening. Anything, any comments, any question you can ask me.
Participants, any questions from your side, you can please post it in the YouTube chat box. Thank you, sir, for your wonderful enlightening session. Thank you. We'll just wait for some questions.
You're welcome.
There are no questions so far. Shall we, Jackson sir? Can we move to the vote of thanks, sir? Shivanyanam sir.
Sure, ma'am.
Thank you, sir. Brishni ma'am, could you please deliver the vote of thanks?
Thank you, ma'am. On behalf of my department, I would like to express my gratitude to our chief guest, Dr. C. Sivanyanam, for giving a lecture on domination-related parameters in graphs. Thank you, sir, for making an excellent presentation and making this webinar very meaningful and interesting. We have learned different types of domination number and the Dometic number for different graphs. And also we study the relationship between the Dometic number and the domination number. You also gave open problem for opening our eye. And thank you so much, sir, for spending time from your busy schedule. And this
It's my
will
pleasure.
okay. And this will use for research student. Thank you, sir. Also, last but not least, I extend my gratitude to all participants of this webinar for your presence. Thank you. Thank you all.
Thank you, Brishni ma'am.
Thank you, ma'am.
Can I leave, ma'am?
Yes, sir. Yeah, the program, we can wind up the program, sir. Thank you, sir. Thanks a lot for your session today.
Thank you, ma'am. Thank you. Thank you very much.